what equation should we start with? We want to use an equation that is simple enough to dive into, to serve as an example, and also relevant to practical cases like the one we are looking at before, the flow around the airplanes. Okay, so the equation we are going to be choosing for this study is this one. So now we are writing partial derivatives, partial u, partial t. So here, u is no longer a function of just time, right? In our previous ODE study, u is just a single function of time, or at most several functions, a vector function of time. Now, u is actually a function of space and time. We are taking partial derivative to time by holding x coordinate to be fixed, right? So if you are able to plot the function of u using x and t, right? So u is going to be some kind of contour on this plot. Then this time derivative is you look at the value of u here and look at how the value of u increases as you move upward on the plot. Upward, not exactly upward, holding x as the same, right? Not sideways. Okay, where if you take partial derivative to x, you're looking at how does u change as you move towards the right in the plot, holding t to be the same and x changes. So the equation we are looking at is du dt plus a constant. Let's start this with a constant times partial u, partial x. I'm going to not write down parentheses x and t, is equal to a certain kappa times partial square u partial x squared. Okay, in ODEs, when we deal with second order derivatives, we were able to convert the second order derivative into first order derivatives, right, by writing out more variables. As we're going to see later, in PDEs, that technique doesn't really help us that much. You can introduce another variable and have another derivative, but after you convert it into ODEs, I mean, it doesn't really help, because you still have as many ODEs as there are number of variables in the time derivative, right? So we have to be able to deal with first order derivatives and the second order derivatives separately. We have different techniques for dealing with them. So this is the equation we are going to be using. Here I wrote a, and sometimes you see people using u also as the constant before the spatial derivative here. So it doesn't really matter that much. Okay, so what's the behavior of this equation? It's a little bit hard to say, but I'm going to first of all introduce you the behavior of this equation when one of these spatial derivative terms are absent. Okay, so let's first look at if the second order derivative is absent. We would have partial u, partial t, plus a times partial u, partial x equal to 0. So let's take a look at what the solution is for that case. I wrote up a MATLAB demo for you to kind of have a visual sense of what the solution is like. So I want to ask one of you to come up and draw me an initial condition. So 1 and 0 is the value of the a and kappa here. So if I set a equal to 1, kappa equal to 0, it's this equation with a equal to 1, right? Okay, so in order for us to have a sense of the solution, right, we need an initial condition, just like for the ODE case. But now the initial condition is not a number, it's a function. Right? When t equal to 0, the u is still a function of x. So here, I'd like to ask one of you to come up and just draw a function of x to serve as an initial condition for my PDE. Somebody come. Just draw on my screen from the left to right of any shape you want.